There is a place on this earth that has never seen sunlight. A place so deep, so still, and so profoundly removed from the world we know that it might as well exist on another planet entirely. It sits beneath the Pacific Ocean, beneath thousands of meters of cold and pressing water, in a darkness so complete that it has no beginning and no end. Most of us will never go there. Most of us will never come close. And yet it is real, and it is here, resting silently at the bottom of our world, full of wonders we are only beginning to understand. Welcome to Sleepy Science. Tonight, we are going somewhere very few humans have ever been. We are descending together into the deepest place on Earth, slowly, gently, one quiet fact at a time. There is nothing you need to do tonight except breathe and listen. The world up here can wait. Tonight, it belongs to the deep. So settle in, let your shoulders drop, let the weight of the day lift away from you, and let the ocean carry you down. The Mariana Trench is the deepest known point on the surface of the Earth. Somewhere in the western Pacific Ocean, not far from a cluster of small islands called the Marianas, the seafloor simply falls away. It drops and keeps dropping, carving a long crescent-shaped wound into the ocean floor that stretches for nearly 2,400 kilometers. At its deepest point, a place called the Challenger Deep, the bottom lies almost 11 kilometers below the surface of the sea. To appreciate what 11 kilometers means in terms of depth, consider this. If you took Mount Everest, the tallest mountain on Earth, and set it down inside the Mariana Trench, its peak would still be more than 2 kilometers underwater. The entire mountain would disappear, and there would still be open water above it. The trench does not simply swallow mountains, it hides them completely and still has room to spare. And yet, for all its vastness, the Mariana Trench is quiet. There are no crashing waves down there, no wind, no storms, just pressure and darkness and the slow passage of time. It has been there for millions of years, waiting patiently beneath the sea. Long before humans walked the earth, the trench was already ancient. It will be there long after we are gone. And somehow, in the middle of the night, that thought is not frightening at all. It is simply calm. The trench was first discovered in the 1800s during a voyage called the Challenger Expedition. In the year 1872, a British ship called HMS Challenger set out on one of the most ambitious scientific voyages in human history. The mission was simple in concept, though extraordinary in practice. The crew would sail across the world's oceans and try to understand what lay beneath them. They would measure depths, collect samples, observe temperatures, and record everything they found. For 3.5 years, the Challenger sailed. And on one remarkable afternoon in the Western Pacific, the crew lowered a weighted line into the water and watched it sink and continue to sink, far beyond anything they had measured before. The line finally went slack at a depth that stunned the scientists aboard. They had found a place in the ocean deeper than anything previously known to exist. They could not have imagined what the trench truly looked like. They had no submarines, no cameras, no instruments that could peer into that darkness. All they had was a line, a weight, and the quiet shock of watching it descend into a depth that seemed to have no end. They named their discovery after the ship itself, the Challenger Deep, and the name has stayed ever since, a small human mark left upon one of the most inhuman places on Earth. Think about what it must have felt like to be on that ship. The sun overhead, the warm Pacific breeze, the ordinary sounds of a working vessel. And then, far below, in a darkness none of them could see, the rope stretching down into the longest silence imaginable. Water pressure at the bottom of the trench is more than 1,000 times greater than the pressure at the surface. At sea level, the air around us presses down on every surface with a certain force. We are so used to this pressure that we do not feel it at all. It is simply the way the world is. But as you descend into the ocean, something changes. For every 10 meters you go deeper, the pressure increases by roughly 1 additional atmosphere. The deeper you go, the more the weight of all the water above pushes down upon everything below. At the bottom of the Mariana Trench, the pressure is approximately 1,100 times greater than it is at the surface. That means every single square centimeter of surface down there is bearing a force that would crush almost anything we might build or bring with us. Steel bends under such pressure. Glass shatters. The human body, without protection, would not survive even a fraction of the descent. And yet, life is down there. Creatures that have never known any other world move quietly through that crushing darkness, as though the pressure were simply the air they breathe. Because for them, it is. Their bodies have evolved over millions of years to match their environment so perfectly that the pressure, to them, is no pressure at all. They are shaped by it, balanced within it, in harmony with a force that would destroy us instantly. There is something deeply restful in that idea, that even in the most extreme place on Earth, life found a way to belong there, to be exactly at home in a world that seems designed for nothing at all. The Challenger Deep sits within the southern end of the trench and is the single deepest point on Earth. The Mariana Trench is long and curving, like a great scar drawn across the bottom of the Pacific by some ancient and patient hand. But within that trench, there are deeper and shallower sections, uneven topography carved by forces operating on geological time. And at the very southern end of the trench, there is one spot that goes deeper than all the others. This is the Challenger Deep. For years, scientists debated exactly how deep the Challenger Deep truly was. Each new expedition with more precise instruments returned a slightly different number. Early measurements placed it at around 10,900 meters. Later surveys pushed that figure slightly higher. More recent efforts using sophisticated sonar mapping systems have recorded depths approaching 10,925 meters, or even more, depending on the methods used. The uncertainty itself is remarkable. We do not know the deepest point on Earth to within even a few meters. The ocean floor is so remote, so difficult to reach and measure precisely, that the trench keeps its secrets with ease. We have mapped the surface of Mars in greater detail than the bottom of our own ocean. The universe outside our world is in some ways better understood than the world beneath our feet. But the Challenger Deep does not mind being mysterious. It has been patient for a very long time. Only a small number of people have ever descended to the bottom of the Mariana Trench. More people have walked on the surface of the Moon than have descended to the deepest point in the ocean. That number is striking. The Moon is roughly 384,000 kilometers away. The Challenger Deep is less than 11 kilometers below the surface of the Pacific. And yet, traveling to the Moon has proved more achievable, or at least more frequently attempted, than reaching the deepest part of our own planet. The first humans to descend to the Challenger Deep were Jacques Piccard and Don Walsh, who made the journey in January of 1960 in a vessel called the Trieste. The Trieste was a bathyscaphe, essentially a steel sphere attached beneath a large float filled with gasoline, which provided buoyancy. It was not graceful, it was not fast. The descent took nearly 5 hours, but when Piccard and Walsh arrived at the bottom, they found something completely unexpected. There were creatures living there, fish or animals that looked like fish, moving calmly across the sediment at the very bottom of the world. Life had found a way into the most extreme corner of the ocean. It was, by any measure, one of the most astonishing moments in the history of exploration. After Piccard and Walsh, the deep went largely unvisited for decades. The difficulty and cost of reaching that depth made regular expeditions nearly impossible. It was not until many years later that other explorers began to follow. Each descent revealed something new. Each journey into the deep returned with questions rather than answers. The bottom of the trench is covered in a soft layer of sediment that has accumulated over millions of years. When you imagine the deepest place on Earth, you might picture bare rock or jagged volcanic formations, or a scene of raw geological violence. But the actual bottom of the Mariana Trench is something far gentler than that. The floor of the Challenger Deep is covered in a pale, silty sediment, a layer of material that has drifted down from the waters above over millions and millions of years. This sediment is made up of tiny particles, the remains of microscopic organisms that lived and died in the sunlit waters far above, mineral grains carried by ocean currents from distant parts of the seafloor, dust blown from continents, even particles from space, tiny bits of cosmic material that have settled gently through the atmosphere, through the ocean, and down to rest at the very bottom of the world. The sediment builds up extremely slowly. In the deep ocean, the rate of accumulation can be as little as a few millimeters per 1,000 years, which means that the upper layers of sediment at the bottom of the trench may represent not thousands but millions of years of quiet, steady deposition. Every centimeter of that pale, soft layer is a record of time, written in the smallest possible script. To disturb it is to disturb history. Submersibles that land on the bottom send small clouds of sediment drifting outward, suspended for a while in the water, then slowly settling back. The trench accepts the disturbance calmly, as it accepts all things, with patience measured in geological ages. Despite the darkness and pressure, the Mariana Trench is home to a surprising variety of life. The idea that nothing could live at the bottom of the Mariana Trench seems perfectly reasonable. No light, immense pressure, near-freezing temperatures, a crushing, silent darkness that has never been touched by sunlight in all of Earth's history. These are not conditions that seem welcoming, and yet the deep is not empty. It is full of life. Not the colorful, charismatic life of the coral reefs, perhaps, but life nonetheless. Strange, adapted, quietly extraordinary creatures that have made the deepest place on Earth their home and seem perfectly content there. Scientists have discovered more than 200 species of organisms in the Mariana Trench alone. Bacteria live in the sediment, processing chemicals in ways that would be impossible anywhere closer to the surface. Tiny crustaceans called amphipods swarm in remarkable numbers, sometimes blanketing the floor in pale, restless crowds. Fish have been filmed swimming calmly through the darkness, their pale bodies and wide eyes giving them an almost ghostly quality. Foraminifera, single-celled organisms encased in delicate shells, drift through the water and settle on the bottom. Life in the deep does not announce itself. It does not glow or flash or call out. It simply exists, quietly and persistently, in the most extreme environment our planet has to offer. And there is something beautiful in that quietness, something that feels, in the dark hours of the night, very much like rest. Amphipods are among the most abundant creatures in the trench, and they can grow surprisingly large. In most parts of the ocean, amphipods are tiny. They are crustaceans, related to shrimp and crabs, and they spend their lives picking through sediment, consuming whatever organic material drifts down from above. In shallow and mid-depth waters, they rarely grow to more than a couple of centimeters. But in the deep ocean, something different happens. In the darkness and cold of the Hadal zone, the deepest parts of the ocean, named after Hades, the mythological underworld, amphipods can reach sizes that would seem impossible to anyone who has only ever seen their shallow water cousins. Some species found in the Mariana Trench have been measured at 28 centimeters or more, the size of a small lobster. This phenomenon of deep-sea gigantism is not fully understood. It may be related to the cold temperatures, which slow metabolism and allow organisms to live longer and grow larger over time. It may be connected to the scarcity of food, which paradoxically seems to favor larger body sizes in some species. Or it may be related to pressure in ways that science has not yet fully untangled. Whatever the cause, the result is striking. The amphipods of the Mariana Trench move through the darkness in great drifting swarms, pale and translucent, collecting around anything that sinks to the bottom. A piece of food dropped into the trench will be surrounded by thousands of them within hours. They are patient creatures, perfectly matched to their world, waiting quietly in the dark. The water temperature at the bottom of the trench stays near freezing all year round. Near the surface, the ocean shifts and changes with the seasons. In summer, the upper layers warm. In winter, they cool. Storms churn the water and mix the temperatures. There is variability, rhythm, a kind of breathing that the surface ocean does throughout the year. But at the bottom of the Mariana Trench, none of that reaches. The water down there is cold and stable, hovering just a few degrees above freezing, regardless of what is happening at the surface. The seasons mean nothing in the deep. The temperature barely changes between one year and the next, or between one decade and the next. Time, in the thermal sense, has essentially stopped. The cold is not hostile, at least not to the creatures that have adapted to it. For deep-sea organisms, the cold is simply the way things are. Their enzymes work at low temperatures. Their membranes are flexible in the cold, rather than stiff. Their chemistry has been shaped over countless generations to function precisely at the temperature of the abyss. There is something settling about that kind of consistency. A place where the temperature is always the same, where nothing shifts or surges, where the cold is steady and deep and reliable. Like the quiet of a very still night, when even the wind has gone to sleep, hydrothermal vents near trenches produce superheated water rich in minerals and support entire ecosystems. Not all of the deep ocean is cold. In some places, where the Earth's internal heat finds pathways through the seafloor, water is heated to extraordinary temperatures and forced upward through cracks and chimneys in the rock. These are hydrothermal vents, and they are among the most remarkable environments on Earth. The water that emerges from a hydrothermal vent can be 300 degrees Celsius or hotter. It does not boil only because the pressure down there is so extreme that even water at that temperature remains liquid. The superheated water is rich in minerals dissolved from the rocks it has passed through on its journey upward. When this mineral-laden water hits the near-freezing water of the deep ocean, the minerals precipitate out and form towering chimneys of dark rock, some of them several meters tall. Because they belch dark, mineral-rich water, they are called black smokers. Around these vents, life flourishes in ways that stunned scientists when they were first discovered in the 1970s. Tube worms, several meters long, sway gently in the currents. White crabs and shrimp cluster in extraordinary numbers. Mats of bacteria cover every available surface. All of it powered not by sunlight, but by the chemical energy in the minerals coming up from the Earth. It was the discovery of hydrothermal vent ecosystems that first made scientists take seriously the possibility of life existing on other worlds. If life can thrive in pitch darkness, at crushing pressures, surviving on chemical energy with no sunlight at all, then the rules for where life can exist had to be rewritten entirely. The Mariana Trench is formed by the movement of tectonic plates, a process that has been ongoing for tens of millions of years. The Earth beneath us is not still. The surface of the planet is divided into enormous sections called tectonic plates, and those plates are always moving, though slowly enough that we cannot feel it in any single lifetime. They drift across the surface of the planet at roughly the speed that your fingernails grow, a few centimeters per year. But over millions of years, even that slow movement produces dramatic results. When two plates meet, one of them typically slides beneath the other in a process called subduction. The plate that goes under bends downward into the Earth's interior, and as it descends, it carves a trench into the ocean floor. The Mariana Trench was formed exactly this way. The Pacific Plate is sliding slowly beneath the Mariana Plate, and where it bends down into the Earth, the ocean floor drops to its greatest depths. This process has been going on for approximately 180 million years in this region of the Pacific. The trench itself, in approximately its current form, has existed for tens of millions of years. It is older than most of the mountain ranges on Earth. It is older than most of the mammals that walk the surface. And it is still forming. The plates are still moving. The Pacific Plate is still descending. The trench may be slightly deeper tomorrow than it was today, and slightly deeper in 1,000 years than it is now. It is not a fixed thing. It is a living, geological process, playing out with a patience that makes human history feel very brief indeed. Earthquakes occur frequently in the Mariana Trench region because of the tectonic activity there. When tectonic plates move against each other, they do not always do so smoothly. The enormous forces involved cause stress to build up along the boundaries between plates, and when that stress is finally released, the result is an earthquake. The Mariana Trench region is one of the most seismically active places on Earth. Earthquakes there are common, though the vast majority of them are small enough that they are felt only by sensitive instruments and not by anything living at the surface. Occasionally, larger events occur, sending shockwaves outward through the Earth and generating tsunamis that can travel thousands of kilometers across the Pacific. But deep in the trench itself, the earthquakes produce a different kind of experience. The pressure waves travel through the water and through the sediment, moving slowly through the dark. Whatever lives down there rides out those tremors as it rides out everything else, with patience, without drama, simply continuing to exist in the way that deep-sea creatures do, without hurry and without alarm. The Earth is restless, but the deep accepts its restlessness calmly, the way a very old and very patient thing accepts the small disturbances of a younger world. Sound travels differently in the deep ocean, and the trench is remarkably full of noise despite its apparent silence. We tend to think of the deep ocean as silent. All that darkness, all that distance from the world above, all that weight of water pressing down, silence seems like the natural result. But the deep ocean is not silent at all. Sound travels through water far more efficiently than it travels through air. In fact, sound moves through water roughly 4.5 times faster than it moves through the atmosphere, and it can carry for extraordinary distances. The deep ocean has a layer called the SOFAR channel, short for sound fixing and ranging, where the conditions are just right for sound to travel particularly efficiently. Whales have been known to communicate across entire ocean basins using this channel. In the Mariana Trench, sounds arrive from extraordinary distances and from every direction: the rumble of earthquakes, the creaking of tectonic plates, the clicks and calls of marine animals far above, the distant churning of propellers from ships passing overhead, the sounds of the surface world, carrying their way down through thousands of meters of water to the bottom of the Earth. Scientists lowering hydrophones, underwater microphones, into the trench have been surprised by how much they recorded. The trench, it turns out, listens to the whole ocean. Everything that makes a sound up there eventually finds its way down here, muffled and distant and transformed by the journey, but present nonetheless. In the deepest part of the ocean, the world is never completely silent. It is full of echoes. A single descent to the bottom of the Challenger Deep takes several hours. The pace of the deep ocean is not our pace. We are creatures of speed and urgency, accustomed to moving through the world quickly, covering distances in hours that once took weeks or months. But the deep does not accommodate speed. A submersible descending to the Challenger Deep travels slowly. The mathematics of the descent are simple, but the experience of them is profound. At a descent rate of around 30 meters per minute, which is typical for a heavily ballasted deep-sea submersible, the journey to the bottom of the Challenger Deep takes close to 6 hours. 6 hours of darkness, of increasing pressure, of the world above growing ever more remote. During that descent, the light fades first. At around 200 meters, the sunlight begins to thin. By 500 meters, it is almost gone. By 1,000 meters, it has vanished completely. From there to the bottom, another 10,000 meters of darkness, the submersible moves through a world that has never seen the sun. The passengers in that vehicle, if there are passengers, must sit with that, with the slowness and the dark and the immensity of what lies all around them. There is no rushing it. There is nothing to do but descend and think and watch the instruments and let the ocean carry you down in its own time. It sounds, in many ways, like falling asleep, a gradual letting go, a slow departure from the familiar world into something quieter and deeper and entirely its own. Many deep-sea creatures in and around the trench produce their own light in a process called bioluminescence. In the darkness below 1,000 meters, there is no light from above, but there is light nonetheless. It comes from within, from the creatures themselves. Bioluminescence is the production of light by living organisms, and it is extraordinarily common in the deep sea. It is, in fact, one of the most common forms of communication and camouflage in the ocean. The majority of deep-sea organisms are thought to produce light in some form. The deep is not simply dark. It is lit from within by 1,000 tiny cold fires, each one produced by a creature going about its business in the permanent night. The mechanisms vary. Some organisms carry light-producing bacteria in specialized organs. Others have chemical reactions that produce light directly in their own tissues. The colors vary too, though most bioluminescence in the deep sea is blue or blue-green, because those wavelengths travel furthest through seawater. Some creatures produce brief flashes, others glow steadily. Others draw intricate patterns of light along their bodies that shift and change as they move. The purposes of bioluminescence are as varied as the creatures that produce it. Some use it to attract prey, dangling a glowing lure in the darkness to draw smaller animals close. Some use it to startle predators with a sudden burst of light. Some use it to communicate with potential mates. Some use it as camouflage, matching the faint glow of the water above them so they cast no shadow for predators below. Down near the Mariana Trench, the bioluminescence is quieter. Many of the creatures at extreme depth glow very faintly, or not at all. But in the waters above the trench, the darkness pulses gently with cold light. A living aurora at the bottom of the sea. The Mariana snailfish is one of the deepest living fish ever recorded, found at depths no other fish have reached. Among the most remarkable residents of the Hadal zone is a small, pale, almost translucent fish called the Mariana snailfish. It belongs to the family Liparidae, and it looks, at first glance, like something unremarkable. A slim, soft-bodied fish, pale as milk, with no scales and wide eyes that seem slightly too large for its head. But the Mariana snailfish holds a record. It has been filmed and collected at depths greater than 8,000 meters, making it one of the deepest living fish ever documented. No other fish has been found deeper. At those pressures, the biochemistry that allows fish to maintain their internal structure becomes extraordinarily challenging, and scientists once believed there was a depth beyond which fish simply could not survive. The Mariana snailfish has been pushing that boundary, existing at depths that were thought impossible for vertebrate life. What makes the snailfish so successful at such extreme depth? In part, it is chemistry. Deep-sea fish, at great pressures, accumulate a compound called trimethylamine oxide, or TMAO, in their tissues. This compound counteracts the effect of pressure on their proteins. keeping the molecules functioning correctly even when the outside world is trying to crush them into a different shape. The deeper the fish lives, the more TMAO it carries. The Mariana snailfish is, at the molecular level, precisely calibrated for the world it inhabits. It lives in groups, moving through the water above the trench floor in small schools, feeding on the tiny crustaceans that swarm in the deep. It is not a dramatic creature. It does not glow or display or perform. It simply lives, deeply and quietly, in the most extreme part of the ocean, perfectly at home. The Challenger Deep has been visited by robotic vehicles many times, each revealing something new. Human beings have visited the Challenger Deep only a handful of times. The engineering challenges, the cost, the risk, all of it makes crewed expeditions extraordinarily difficult. But robotic vehicles, unmanned submersibles guided by tethers or programmed with autonomous navigation, have made the journey many more times. Each of these missions has returned with something unexpected. Early robotic surveys found sediment samples filled with microorganisms. Later missions photographed animals no one had ever seen before. Sonar surveys began to reveal the detailed topography of the trench floor, showing ridges and valleys and geological features invisible to instruments above. One of the most remarkable robotic surveys used a new generation of autonomous vehicles equipped with high-resolution cameras and sophisticated sampling equipment. These vehicles descended slowly, mapping as they went, and returned with footage of creatures moving calmly through the darkness. Snailfish, amphipods, small holothurians, the soft-bodied relatives of sea cucumbers drifting slowly across the pale sediment, all of them living their unobserved lives, utterly indifferent to the machines that had descended to witness them. Each time we send a vehicle into the deep, the ocean gives up a small portion of its mystery. And each time, it reveals how much more mystery remains. The trench is generous with its secrets. It offers them one at a time, slowly, in its own order, on its own schedule. The pressure at the bottom of the trench is so great that it compresses seawater itself, making the deep ocean denser than surface water. Water is often thought of as incompressible. In everyday life, this is essentially true. You cannot squeeze a glass of water into a smaller volume with any force your hands could produce. But at the pressures found in the Mariana Trench, even water is compressed. The molecules are pushed slightly closer together, and the water at the very bottom of the ocean is measurably denser than the water at the surface. This might seem like a small and technical point, but it has real implications for how the deep ocean works. The density of the deep water affects how currents move, how heat is distributed, and how the ocean circulates over time. The great deep currents that move through the world's oceans, the slow rivers of cold, dense water that flow along the ocean floor, are driven in part by this density difference. The bottom of the Mariana Trench is part of a global system. The compressed, cold, dense water down there is one node in the largest circulatory system on Earth, the movement of water that connects all the world's oceans and plays a profound role in regulating climate. The deep is not isolated. It is part of everything. It breathes with the whole ocean, and the whole ocean breathes with the whole planet. The depth and the surface are always in conversation, even if that conversation moves on timescales of centuries. Scientists have found plastic waste and other pollutants at the very bottom of the Mariana Trench. Among the most sobering discoveries made in the Mariana Trench in recent years has been the presence of plastic. In samples collected from the deepest parts of the trench, and in the bodies of animals living there, scientists have found microplastics, tiny fragments of synthetic materials that have made their way from the surface world all the way to the bottom of the ocean. It is a sobering reminder of how connected we are to even the most remote places on Earth. The plastic that enters the ocean from rivers and coastlines does not simply float on the surface. Some of it breaks down into tiny fragments, small enough to be ingested by marine organisms, and those fragments are carried by currents and by the feeding behavior of animals steadily downward through the water column. In time, they arrive at the bottom. In 2018, researchers announced that they had found pollutants in amphipods collected from the Mariana Trench at levels comparable to what you might find in the most polluted coastal environments on Earth. The chemicals they found included polychlorinated biphenyls and other persistent organic pollutants, substances that are no longer manufactured but which linger in the environment for decades or centuries. The deep ocean was once thought to be beyond the reach of human activity, a place so remote, so deep, so difficult to access that our influence could never penetrate it. That idea can no longer be maintained. Even the Mariana Trench carries the fingerprint of the surface world. But knowing this is not cause for despair, it is cause for care. The trench has been patient with us. It will, one hopes, be patient still. The trench is located in a region of the Pacific called the Western Pacific Warm Pool, the warmest body of ocean water on Earth at the surface. There is a beautiful contrast at work in the geography of the Mariana Trench. The surface waters in the region where the trench is found are some of the warmest in any ocean on Earth. The Western Pacific Warm Pool, as it is known, sits just above one of the coldest and most pressure-compressed bodies of water on the planet, warmth above and below it, at a distance of nearly 11 kilometers, near freezing darkness. The warm surface waters fuel some of the most intense tropical weather systems on Earth. The Western Pacific is the birthplace of typhoons, the same storms that are called hurricanes when they form in the Atlantic. The heat and moisture in those surface waters power enormous rotating storms that can be hundreds of kilometers wide and carry winds of extraordinary speed. None of that, not the warmth, not the storms, not the turmoil of the tropical surface, reaches the bottom of the trench. The two worlds are separated by 10,000 meters of water and countless layers of ocean, each one slightly cooler and darker than the one above it. The bottom of the trench is as unaware of tropical typhoons as we are of the slow grinding of tectonic plates. The surface world rages and shines. The deep world is still. Both exist simultaneously, separated by distance but sharing the same planet. One reaching toward the sun, the other resting in permanent night. The Mariana Trench is home to Xenophyophores, some of the largest individual cells on Earth. Among the most unusual inhabitants of the Mariana Trench are organisms called Xenophyophores. They are single-celled organisms, but they are unlike any single cell you might imagine. They are visible to the naked eye. In fact, some of them are enormous by the standards of any cell, growing to 20 centimeters or more in diameter. They are, in this respect, the largest individual cells known to exist anywhere on Earth. Xenophyophores live on the seafloor, forming irregular, branching structures that resemble small sponges or lumps of pale material. They collect particles from the water and from the sediment around them, incorporating everything from bits of mineral to tiny shells of dead organisms into their own bodies. Over time, they build up complex, fragile architectures of accumulated material. Despite their large size, they are delicate. The first time researchers tried to collect Xenophyophores from the deep, the organisms fell apart during the ascent, unable to survive the change in pressure and handling. Later, expeditions used more careful techniques to preserve them, and scientists were able to study them in more detail. They do not move. They do not pursue prey. They simply sit on the sediment and collect what comes to them, growing slowly over a lifetime that may span years. They are, in their way, perfect residents of the deep, patient, still, present. A submersible window must withstand the same pressure as 11,000 meters of water bearing down on a small pane of glass. The engineering required to descend to the Challenger Deep is among the most demanding in the world. The pressure at the bottom of the trench would shatter conventional materials, crush conventional structures, and flood any vessel not specifically designed to withstand it. Building a vehicle capable of reaching those depths and returning is an exercise in precision and care. The viewing ports, the windows through which passengers observe the deep, must be among the most carefully engineered pieces of glass or acrylic on Earth. They must withstand the full pressure of the water column above them, which at the bottom of the Challenger Deep means a force of roughly 1,100 atmospheres bearing down on every surface. A viewport, a few centimeters wide, is subjected to forces equivalent to the weight of dozens of fully loaded trucks. The solution involves conical shapes, in which the material is pressed more firmly into its seal by the pressure itself, rather than being forced out of it. The greater the pressure, the tighter the fit. It is an elegant piece of engineering, using the very force that threatens the vessel to reinforce its integrity. Even so, every descent is a test. The deep does not forgive small errors. Every weld, every seal, every piece of hardware on a deep-sea submersible is inspected with extraordinary care before each dive. And even then, the vehicle is trusted only because of what it has survived before. James Cameron made a solo descent to the Challenger Deep in 2012, the first solo crewed dive to that depth. Among the handful of humans who have descended to the Challenger Deep is the filmmaker James Cameron, who in March of 2012 became the first person to make a solo crewed dive to the deepest point on Earth. Cameron had spent years working with engineers to design a purpose-built submersible called the Deep Sea Challenger. It was a remarkable vehicle, narrow and vertical rather than the traditional spherical shape, designed to descend quickly and use its time at the bottom efficiently. The descent took approximately 2 hours and 36 minutes. At the bottom, Cameron spent nearly 3 hours exploring the trench floor with cameras and scientific instruments, collecting samples of sediment and organisms. He described the bottom as a barren, lunar landscape, though not without life. Amphipods were visible, and the sediment stretched away in all directions, pale and still, into a darkness that his lights could not fully penetrate. What Cameron brought back, beyond the samples and the footage, was a sense of the place, the quiet of it, the immensity of the darkness. The way the trench sat at the bottom of its own world, complete and undisturbed, barely touched by the descent of a small vehicle and one curious human. After spending time at the bottom, he released the ballast weights that held his vehicle down and rose slowly back toward the surface, back toward light, back toward the world of noise and weather and ordinary things. The journey upward, after the deep, must feel like waking from a very particular kind of dream. The Mariana Trench may hold clues about the origins of life on Earth. Life began on this planet sometime between 3.5 and 4 billion years ago, in conditions that scientists are still working to understand. One of the leading theories about where and how life first appeared points to the deep ocean, specifically to environments very much like hydrothermal vents. The chemistry of deep-sea hydrothermal vents is extraordinary. Hot, mineral-rich water mixing with cold seawater creates strong temperature gradients and a constant flow of chemical energy. The minerals themselves, things like iron and sulfur and hydrogen, can participate in complex chemical reactions that, under the right conditions, begin to resemble the chemistry of living things. Membranes form spontaneously. Molecules polymerize. Complex organic chemicals assemble themselves from simpler components. Some researchers argue that life did not just originate near hydrothermal vents. It originated in the pores and crevices of the rocks around those vents, in tiny chambers where concentrations could build up and reactions could occur over geological timescales. The ancestors of all life on Earth, on this view, were not swimming freely in a primordial ocean. They were huddled in the warm, mineral-rich darkness of the deep sea floor, in conditions not entirely unlike those found near the Mariana Trench today. If this is true, then the deep is not just the deepest place on Earth. It is in some sense the oldest place, the place where everything began, and we are all, in the most literal sense, children of the deep. There are places within the trench called Hadal zones, the deepest ecological regions of the ocean, beginning at 6,000 meters. The ocean is divided into zones based on depth, each one with its own character, its own community of life, its own particular quality of darkness and pressure and cold. The shallowest is the sunlit zone, where photosynthesis is possible and life is richest. Below that comes the twilight zone, where light fades. Then the midnight zone, completely dark. Then the abyssal zone, the broad, flat plains of the deep ocean floor. And below the abyssal zone, beginning at around 6,000 meters, is the Hadal zone. Named for the Greek underworld, the Hadal zone encompasses all the ocean's deepest trenches, including the Mariana. It is the least studied region of the ocean, the least understood, and the least visited. Only a small fraction of the Hadal zone has been explored in any detail. Within the Hadal zone, the conditions are severe enough that many organisms cannot survive, but those that have adapted to live there are remarkable for their specialization. Hadal species often differ significantly from their relatives at shallower depths, shaped by millions of years of evolution under conditions unlike anything else on Earth. They are, in a sense, creatures of another world, one that exists on our own planet but operates by its own rules. The Hadal zone is the frontier of ocean science. Every new expedition there expands the map, adds new species to the list, raises new questions about how life works at extremes. It is a place where our knowledge is thin and the ocean's secrets are deepest. Currents in the deep ocean move extremely slowly, circulating water on timescales of hundreds and even thousands of years. At the surface, the ocean moves. Currents driven by wind and temperature carry water around the globe on timescales of years or decades. Gyres rotate in the major ocean basins, carrying warm and cold water in enormous loops. The Gulf Stream transports heat from the tropics toward northern Europe. The surface ocean is dynamic, changeable, responsive. The deep ocean is different. Below the thermocline, the boundary between warm surface water and cold deep water, the ocean moves on a different timescale entirely. The thermohaline circulation, sometimes called the ocean conveyor belt, drives the slow movement of deep water around the planet. Cold, dense water sinks at high latitudes and flows slowly along the ocean floor toward the tropics. The journey from the North Atlantic to the deep Pacific and back can take 1,000 years or more. The water currently sitting at the bottom of the Mariana Trench last saw the surface centuries ago, or possibly longer. It has been sitting in the deep, under pressure, in the dark, moving imperceptibly slowly through its journey around the ocean. By the time it returns to the surface, centuries will have passed. This is the time scale of the deep ocean, not days or seasons or human generations, but centuries. The deep operates on a patience that makes almost everything else seem rushed. Some organisms in the deep ocean can survive without oxygen, living in what are called anoxic environments. Life, as we typically understand it, requires oxygen. The process of respiration that powers our cells and the cells of most living things depends on oxygen being available. When oxygen runs out, life, for most organisms, is no longer possible. But in some parts of the deep ocean, oxygen is scarce or absent. Zones of low oxygen, called oxygen minimum zones, develop where organic material decomposes faster than currents can replenish the oxygen supply. And in some extreme deep environments, oxygen is essentially absent altogether. Life is there anyway. Microorganisms called anaerobic bacteria have found ways to derive energy from chemical reactions that do not require oxygen. Some use sulfate, some use nitrate, some process methane. They have effectively rewritten the rules of metabolism, finding pathways through the chemistry of the deep that work perfectly well without the molecule that almost all surface life depends on. These organisms are not merely curiosities. They play a crucial role in the chemistry of the deep ocean, cycling nutrients and chemicals through the sediment in ways that affect the entire ocean system. And their existence expands, once again, our understanding of where life can exist, not just on Earth, but potentially on other worlds. If life on Earth can survive without oxygen, in darkness, under crushing pressure, then the universe of possible habitats becomes very wide indeed. The Mariana Trench sits within an area of the Pacific known for extreme geological activity, sometimes called the Ring of Fire. Around the edges of the Pacific Ocean, a chain of volcanoes, earthquake zones, and tectonic boundaries forms a rough circle that geologists call the Ring of Fire. It stretches from the west coast of the Americas, across Alaska, down through Japan and the Philippines, through New Zealand, and back across the Pacific. Along this ring, the majority of the world's most powerful earthquakes and volcanic eruptions occur. The Mariana Trench sits within the Ring of Fire. The same tectonic processes that have created the trench are also responsible for the volcanic archipelagos of the Marianas Islands above it, and for the earthquakes that occasionally shake the region. The deep and the surface are connected here by forces that operate far beneath both. The Ring of Fire has shaped the Pacific in fundamental ways. The islands that dot the western Pacific, many of them formed by volcanic activity, are the surface expression of the same geological machinery that created the trench. The volcanoes and the abyss are siblings, born of the same tectonic process, one reaching upward toward the sky, while the other descends into the earth. It is a place of extraordinary geological energy, and yet, from the bottom of the trench, none of that drama is visible. The volcanic islands are 10 kilometers above. The tectonic machinery is happening in the rock far below. At the bottom of the trench, everything is still. The earth moves around it, but the deep sits in its own quiet, at the center of everything. Scientists use acoustic sonar to map the seafloor, painting pictures of the trench in sound. We cannot see the bottom of the Mariana Trench from above. The water is too deep, too dark, too opaque for any kind of light-based observation from the surface. But sound is a different matter. Sound travels through water extremely well, and by sending pulses of sound downward and measuring how long it takes for the echoes to return, scientists can build detailed three-dimensional maps of the seafloor. This technique, called multi-beam sonar, involves ships towing arrays of sound emitters and receivers that cover wide swaths of the seafloor in a single pass. The returning echoes are processed by computers to produce detailed maps showing depth, topography, and the character of the seafloor surface. Over decades of survey work, these maps have revealed the extraordinary complexity of the trench. The Challenger Deep is not a simple flat bowl. It has ridges and valleys, different sections at slightly different depths, geological features carved by the ongoing collision of tectonic plates. The maps show terraced slopes, sediment flows, and geological structures that take millions of years to form. The deep, seen through sonar, is as complex and detailed as any landscape on the surface. And yet, for all that the maps reveal, they are still maps. They show the shape of the place, but not its texture, not the living creatures moving across the sediment, not the quality of the darkness, or the pressure, or the cold. The map is not the territory. The trench is always larger and more detailed and more itself than any representation of it can convey. The first organisms discovered at extreme ocean depths helped redefine what scientists thought was possible for life. When the very first deep-sea expeditions lowered dredges and nets into the deep ocean in the 19th century, most scientists expected to find nothing. The prevailing theory, championed by the influential naturalist Edward Forbes, held that the deep ocean below about 500 meters was completely lifeless, an azoic zone. No light, no warmth, too much pressure. Nothing could live there. Forbes was wrong. As the Challenger expedition and others dredged up material from increasingly great depths, they found organisms, worms, crustaceans, echinoderms. Simple but unmistakably living creatures, recovered from depths that were supposed to be completely barren. Each new discovery pushed the limit further down. The boundary of lifelessness kept retreating as the expeditions went deeper. And eventually, when technology allowed humans and robots to visit the very deepest places, the final revelation came. Life was not just present in the deep. It was abundant, specialized, and thriving on its own terms. The story of discovering life in the deep ocean is a story about the danger of assuming we know where the boundaries of the possible lie. Again and again, the ocean pushed those boundaries outward. Again and again, life was found where it was not supposed to be. And each time, the world became a little larger, a little more full of possibilities, a little more surprising than it was before. Water from the surface takes centuries to reach the bottom of the Mariana Trench through the slow circulation of the deep ocean. The water at the bottom of the trench has been on a very long journey. It did not begin at the bottom. It began at the surface, somewhere in the cold waters of the high latitudes, perhaps the North Atlantic or the waters around Antarctica. There, chilled by the polar air and made dense by its salinity, it sank. It began to descend through the water column, driven by its own density, slowly making its way toward the ocean floor. From there, it followed the subtle gradients of the deep ocean, moving imperceptibly slowly toward the Pacific. The journey took centuries, perhaps more. The water flowed along the ocean floor, guided by underwater topography, sinking into the deepest parts of the ocean basin, until finally it found its way into the network of deep trenches that cuts the Pacific floor. And eventually, some of it settled at the bottom of the Mariana Trench. The water, you might imagine sitting at the very bottom of the Challenger Deep, last touched the surface of the ocean hundreds of years ago. It has been traveling ever since, moving through the dark in a journey measured not in miles per hour, but in years per meter. When it finally returns to the surface, upwelling in some distant part of the ocean, it will carry with it the chemistry of the deep, the minerals and nutrients it has collected on its long journey. And it will warm in the sunlight, and gas will dissolve into it, and eventually it will be ready to sink again, beginning another journey, measured in centuries. Expedition ships above the trench can feel very alone, even in the middle of a busy ocean. There is a particular kind of solitude that comes from being on a research vessel above the Mariana Trench. The Pacific is an enormous ocean. The region near the trench is remote from major shipping lanes and far from the coasts. In every direction, the horizon offers only water. Scientists who have worked on such expeditions describe a distinct quality to the experience: the awareness that below you, impossibly far below, is the deepest place on Earth, that the seafloor beneath the ship is not close at all, but separated by a distance greater than most people travel in their daily lives. The ocean here is not shallow. It is the opposite of shallow. It is the most profound depth our planet possesses. And yet, standing on the deck of a research ship, the ocean looks the same as it always does. Waves, wind, the broad horizon, the sun rising and setting on schedule. None of the depth below is visible or felt. The immensity of the trench is entirely invisible from the surface. This is, perhaps, one of the most humbling things about the deep. Not just that it is there, but that it is invisible. That you can float directly above one of the most extraordinary places on Earth and see nothing, feel nothing, know nothing of it, unless you already know to look. The world contains depths that are completely hidden from us, even when we are standing directly above them. Some species in the trench have adapted transparent bodies, which may offer protection in a world with no light to reflect. In the permanent darkness of the deep ocean, being visible is often dangerous. A brightly colored or opaque body is easy for a predator to see, especially if bioluminescence is nearby. Many deep-sea organisms have evolved strategies to reduce their visibility. Some are jet black, absorbing any light that hits them. Some are red, a color that appears black at depth because red wavelengths of light do not penetrate deeply, and some are transparent. Transparency in the deep ocean is a remarkable adaptation. An organism with a completely clear body essentially disappears. Its tissues pass light through them rather than reflecting it, making the creature effectively invisible to any eye that might be searching for it. The only parts that tend to remain visible are the digestive organs, which cannot easily be made transparent because they contain food and other opaque materials. Near the Mariana Trench, transparent organisms drift through the water in astonishing variety. Small crustaceans with completely clear shells reveal their internal organs and heart beating within. Jellyfish hover with transparent bells, their trailing tentacles almost invisible until they are touched. Fish with clear bodies glide through the dark, barely more visible than the water itself. They are not hiding, they are simply not there in the visual sense. They have made themselves out of nothing, in a place where nothing is the dominant color. The Mariana Trench creates its own unique water chemistry, distinct from the open ocean above. Water chemistry is not uniform throughout the ocean. Different depths, temperatures, pressures, and biological communities all influence the chemical composition of the water. And in the Mariana Trench, where conditions are unlike anywhere else on Earth, the chemistry of the water has its own particular character. Dissolved oxygen levels at the very bottom of the trench are low, but not absent. The slow supply of oxygen through deep water circulation is just enough to support the aerobic organisms that live there, though those organisms have typically evolved to function efficiently with whatever oxygen is available. Dissolved carbon dioxide levels are higher at depth, affecting the acidity of the water. The deep is generally more acidic than the surface, in part because carbon dioxide is more soluble at lower temperatures and higher pressures. This increased acidity has important implications for organisms that build shells or skeletons from calcium carbonate. Many creatures that thrive in shallower water would find their shells dissolving in the deep. Below a certain depth, called the carbonate compensation depth, calcium carbonate does not persist, it simply dissolves. This is one of the reasons that the sediment at the very bottom of the trench is not dominated by the calcium carbonate shells of tiny organisms, as it is at many shallower locations, but instead by silica and clay. The chemistry of the deep is its own language, written in dissolved gases and minerals, and the quiet processes of organisms making their living at extremes. The deepest parts of the ocean were once thought to be static and unchanging, but we now know they are dynamic. For a long time, the deep ocean was imagined as a kind of timeless realm, a place where nothing much happened and nothing much changed. The stillness and the slow currents suggested a world frozen in its own permanence, too remote and too extreme for any of the dynamism of the surface world to penetrate. We know now that this was wrong. The deep ocean is dynamic, not at the timescale of days or seasons, but at the timescale of decades and centuries and geological epochs. Deep ocean currents shift as the climate changes, altering the flow of water and the distribution of nutrients and oxygen. The chemistry of the deep changes as the surface ocean absorbs more carbon dioxide from the atmosphere. Tectonic activity reshapes the floor of the trench over geological time. Even at shorter timescales, the deep is not still. Organic material rains down from above in what scientists call marine snow, a constant gentle fall of particles from the sunlit world to the dark floor. Large organisms die in the water above and sink to the bottom as food for the scavenging community of the deep. Occasionally, entire whale carcasses arrive at the seafloor, providing a sudden bonanza that supports a specialized community of organisms for years. These events, called whale falls, create their own temporary ecosystems. The whale's body passes through stages of decomposition, each stage supporting different communities. Scavengers strip the soft tissue, then organisms break down the bones, and finally, sulfur-reducing bacteria colonize the remaining material, creating a chemistry not unlike that of a hydrothermal vent. A whale fall can support life at the deep seafloor for decades. The deep listens to the surface. It changes with it, slowly, on its own terms. Light from the sun never reaches the bottom of the trench, making it one of the last truly dark places on Earth. We live in a world saturated with light. Even at night, our streets and buildings and screens push brightness into every corner. The night sky carries starlight and moonlight. The darkest places we tend to encounter are temporary: a power outage, a windowless room, a momentary closing of the eyes. But the bottom of the Mariana Trench has never seen light. Not once, in all the hundreds of millions of years since the trench was formed. The sun rises and sets every day above the Pacific, painting the surface of the water gold and then fading again to dark. The surface of the ocean sparkles and shimmers with every photon it receives, and 10,000 meters below, not a single one of those photons arrives. Not a flicker, not a trace. The darkness of the trench is not the darkness of a room with the lights off. It is the darkness of a place that has never known light, that has no reference for it, that carries no memory of it. It is a different quality of darkness from anything we experience. A darkness that is not temporary or circumstantial, but simply the permanent and total condition of a place. And yet life is there. Creatures that have never seen light, that have evolved entirely in its absence, that have no more need for it than a forest has for the ocean. They are built for the dark. They belong to it. The darkness, for them, is not an absence. It is simply what the world is. There are underwater mountain ranges inside the Mariana Trench that have never been seen by human eyes. The Mariana Trench is not just a flat-bottomed crack in the sea floor. Its interior topography is complex and varied, shaped by the same tectonic forces that created the trench itself. Sonar mapping has revealed ridges running across the floor of the trench, raised walls along its sides, and sediment flows that have reshaped its surface over time. Some of these internal features are significant in scale. Ridges within the trench rise hundreds of meters above the surrounding floor. Walls along the trench's flanks slope steeply downward, creating a landscape of dramatic vertical relief. Some sections of the trench floor are divided into separate basins by internal ridges, each one slightly different in depth and character. These features have never been seen directly by human eyes. Sonar gives us their shape, their dimensions, their rough topography. But the detail, the texture of the rock, the life that might cling to the walls, the color and character of the sediment in different sections, all of that is known only to the darkness and to whatever lives within it. The exploration of these interior features is still in its early stages. Each new sonar survey reveals more complexity than the last. The more we map the trench, the more there is to map. The deep rewards careful attention with more and more detail until the map begins to approach the territory itself, and even then falls short. The sediment of the trench contains chemical signals from events that occurred millions of years ago. The pale sediment that covers the floor of the Challenger Deep is a record. Not a written record, not something that can be read at a glance, but a chemical and physical archive that encodes the history of the ocean above it in the materials that sank to the bottom over millions of years. Scientists who study deep-sea sediments can extract that archive carefully. They drill down through the layers, taking core samples that represent time, with the deepest layers being the oldest. By analyzing the chemical composition of the sediment at different depths, they can reconstruct conditions in the past ocean. The temperature, the chemistry, the types of organisms that were living in the surface waters above, the presence or absence of oxygen. Even the chemical fingerprints of major geological events like volcanic eruptions or asteroid impacts. The sediment of the Mariana Trench holds tens of millions of years of this history. Somewhere in those layers is the chemical record of the mass extinction that ended the dinosaurs 66 million years ago, when an asteroid struck the Earth and changed everything. Somewhere in those layers is the record of the Paleocene-Eocene thermal maximum, when the Earth's temperature spiked dramatically and the oceans became more acidic. All of it is there, recorded in the quiet accumulation of particles over geological time. The floor of the trench is not just a place, it is a memory. At the deepest points in the ocean, creatures live in a world shaped entirely by chemistry, not sunlight. The energy that powers almost all life on Earth's surface comes from the sun. Plants capture sunlight and convert it into chemical energy. Animals eat the plants. Other animals eat those animals. The sun is the source, and everything downstream of it depends on photosynthesis, directly or indirectly. In the deep ocean, and particularly in the Hadal zone, sunlight is irrelevant. There is none. The organisms down there cannot depend on photosynthesis, because photosynthesis requires light. Instead, they depend on something else, on chemistry. Two main pathways supply energy to deep-sea communities. The first is the slow rain of organic material from above. Dead organisms, fecal particles, fragments of algae, and other material that sinks through the water column. This material carries the chemical energy originally captured by photosynthesis at the surface, but transformed and concentrated during its journey downward. Deep-sea communities that depend on this material are ultimately still solar-powered, but at several removes. The second pathway is chemosynthesis. Near hydrothermal vents and cold seeps, microorganisms can derive energy directly from chemical reactions, particularly the oxidation of hydrogen sulfide and other compounds. These organisms form the base of food webs that are entirely independent of the sun. They are the only organisms on Earth that live completely outside the solar energy budget, sustained by the heat and chemistry of the Earth itself. These communities are among the most independent forms of life known. They belong to the deep in the most complete sense. They were never part of the surface world. They do not need the sun. They have their own energy, their own darkness, their own way of being alive in the world. Exploring the deep ocean remains one of the greatest scientific challenges of the 21st century. We have sent spacecraft to the Moon and to Mars. We have mapped the surface of Venus through clouds of sulfuric acid using radar. We have launched telescopes into orbit that can see galaxies billions of light years away. We have probed the structure of subatomic particles and decoded the genome of thousands of species. And yet less than 20% of the ocean floor has been mapped with any resolution. The Hadal zone, the deepest region of the ocean, has been visited only a handful of times by crewed vehicles. Vast stretches of the deep ocean floor have never been directly observed at all. By many measures, the deep ocean is the least understood environment on Earth. The challenges are real. Building vehicles that can withstand the pressure of the deep is difficult and expensive. Operating in an environment where communication is nearly impossible, where instruments fail, where everything must function perfectly without any possibility of outside help, demands extraordinary engineering. Funding deep-sea research competes with other scientific priorities and often comes up short, but the scientists who dedicate their careers to the deep do not seem discouraged by this. They describe their work the way explorers have always described the frontier, with a sense of privilege, of standing at the edge of what is known and looking outward into what is not. Every dive is a first. Every sample brings something new. Every descent into the dark is a journey into a world that has never been seen before. The snailfish, the deepest living fish known to science, has no scales and skin, so delicate it tears if handled roughly. Imagine a creature built entirely for depth, not for strength or speed or dramatic display, but simply for existing at a pressure that would crush almost any other vertebrate on Earth. The Mariana snailfish has given up many of the features common to fish that live in the light. Its scales are gone, replaced by a soft, slightly gelatinous skin. Its bones are flexible, not the rigid structures of surface fish, but something more yielding, less likely to collapse under pressure. Its color is a pale, almost translucent white or faintly pinkish, depending on the individual and the light you use to look at it. Its eyes are relatively large, although in the absolute darkness of the deep, even large eyes can detect only the bioluminescent flickers of other creatures. It is a soft-looking animal, delicate in ways that seem contradictory for something living at such extremes. Researchers who have successfully collected snailfish from the deep report that they are nearly impossible to preserve in recognizable form. The change in pressure from the deep to the surface is devastating to tissues adapted for depth. The fish essentially fall apart during the ascent, their bodies unable to maintain their structure in the very different conditions of shallow water. They are creatures of a specific world, and they cannot leave it. They are as precisely matched to their environment as the environment is to them. Perfectly placed, perfectly adapted, belonging to the deep as completely as any creature belongs to any place on Earth. The Mariana Trench has inspired poetry, fiction, and scientific curiosity for as long as it has been known to exist. Since the Challenger expedition first measured the extraordinary depth of the trench, it has exercised a hold on human imagination that goes far beyond the merely scientific. There is something about the existence of such a place, right here on our own planet, hidden beneath the ordinary-looking surface of the Pacific, that resonates with something deep in us. The idea of the trench has appeared in novels, in films, in poems, in the quiet contemplations of people who have simply heard about it and found themselves unable to stop thinking about it. It represents, in the imagination of many, the ultimate unknown, the limit of the knowable, the place where the ordinary world ends and something else begins. But it is not really unknowable. It is simply hard to reach. And with every expedition, every robotic survey, every carefully collected sample, the mystery shrinks a little, and the knowledge grows. The trench was unknown to humans until the 1800s. It was completely unmapped until the 20th century. It was first visited in person only in 1960. And now we know its shape, its residence, its chemistry, its geology, with a detail that would have astonished the sailors who first lowered a weighted line into its darkness. The mystery does not disappear with knowledge. It transforms. The more we know about the trench, the more remarkable it becomes. Not less, but more. Knowledge of the deep only deepens the wonder. The ocean as a whole covers more than 70% of the Earth's surface, and most of it remains unexplored. The Mariana Trench is the most extreme point in a vast and largely unknown world. The ocean covers about 71% of the Earth's surface, an area so large that all the continents could fit within it with room to spare. And the average depth of the ocean is around 3,800 meters. It is not a shallow place. The ocean is, by volume, the dominant habitat on Earth. Yet, it remains the least explored. Scientists estimate that more than 80% of the ocean floor has never been observed directly. That means the majority of our planet's surface, including its mountains, valleys, volcanoes, and plains, has never been seen. We have a better map of the surface of the Moon or the surface of Mars than we have of the bottom of our own ocean. This is changing. New technologies, including long-range autonomous underwater vehicles and improved sonar systems, are accelerating the mapping of the seafloor. Each year, a little more of the unknown becomes known. Each new survey reveals terrain and life and geological features that had never previously been documented. But the pace of exploration is slow relative to the size of the ocean, and the ocean is very patient. It does not hurry the explorers. It waits, as it has always waited, in its own darkness and cold and immensity, carrying its secrets with perfect equanimity. Foraminifera, tiny shelled organisms, rain down onto the trench floor in vast numbers every day. Among the most numerous contributors to the sediment of the deep ocean are organisms so small they are invisible to the naked eye. Foraminifera are single-celled organisms, relatives of amoebas, that build intricate shells around themselves from calcium carbonate or other materials. They drift through the sunlit upper ocean in staggering numbers, billions of them in every cubic meter of water in productive regions. They feed, they reproduce, they live their brief lives, and then they die. When they die, their shells sink. They drift slowly downward through the water column, a constant gentle snowfall of tiny structures, each one no larger than a grain of sand, each one a small work of biological architecture. Some are spiraled, some are multi-chambered, their internal structure arranged in patterns of remarkable geometric elegance. Each shell is a record of the organism that built it and of the water conditions in which it lived. After sinking through potentially thousands of meters of ocean, they arrive at the floor of the deep sea. In shallower regions, their shells accumulate and form thick layers of sediment. But in the very deepest parts of the ocean, the increased acidity and pressure dissolve calcium carbonate before it can settle, and the shells never arrive. The sediment at the very bottom of the Mariana Trench is shaped in part by this chemistry of dissolution, which filters out the calcium carbonate remains and leaves only the most resistant materials behind. But in the waters above the trench, the foraminifera fall continuously. It is one of the most quiet and persistent processes in the ocean. No sound, no light, just the slow, steady rain of tiny shells drifting downward from the living world above into the dark world below, a connection between two realms as gentle and continuous as breathing. Cold seeps, like hydrothermal vents, create oases of life in the deep by releasing chemicals from the sea floor. Not all the chemistry that sustains deep-sea life comes from hot water venting upward from below. In some places, along the continental margins, and in the deep trenches, cold water seeps slowly upward through cracks and fissures in the rock, carrying with it methane and hydrogen sulfide dissolved from sediments rich in organic material. These are cold seeps, and like hydrothermal vents, they support rich communities of life entirely independent of the sun. Cold seeps were first discovered in the 1980s in the Gulf of Mexico, and they have since been found in many locations around the world's oceans, including near subduction zones like the one that created the Mariana Trench. Near these seeps, bacteria use the chemical energy in methane and hydrogen sulfide to produce organic material, which then forms the base of a food web, unlike anything in the sunlit ocean above. Tube worms cluster around cold seeps, some of them reaching several meters in length, living for centuries. Clams with unusual biochemistry colonize the sediment nearby. Mussels form dense beds. Small crabs and other crustaceans move through the community, feeding on bacteria and other organisms. The cold seep community is slower and quieter than a hydrothermal vent community. The water is cold, the chemicals arrive more slowly, the energy is more diffuse. The organisms that live there tend to grow slowly and live long. A tube worm at a cold seep may live for 200 years or more, growing slowly in the dark, sustained by the chemistry of the earth. These communities are among the most ancient feeling places in the ocean. Not ancient in the way that a museum is ancient, but alive in their ancientness, still doing what they have done for millions of years, still turning the Earth's chemistry into life. The Mariana Trench plays a role in the global carbon cycle by trapping organic carbon in its deep sediments. Carbon moves through the Earth's systems in an enormous and slow cycle. It enters the atmosphere as carbon dioxide. Plants and ocean phytoplankton absorb it and convert it into organic material through photosynthesis. That material is eaten, decays, and some of it returns to the atmosphere, but some fraction of it escapes this cycle entirely. In the ocean, a portion of the organic material produced in the sunlit surface waters sinks before it can be fully decomposed. It drifts downward as marine snow, as the bodies of dead organisms, as particles of every description, and some of it reaches the deep seafloor before it is broken down. There, it is buried in sediment. And carbon that is buried in deep-sea sediment can remain there for millions of years, effectively removed from the active carbon cycle. The Mariana Trench, by virtue of its depth and the unusual chemistry of its sediment, plays a role in this carbon burial process. The organic material that arrives at the trench floor is partially processed by the microbial communities living in and on the sediment, but some of it is buried, incorporated into the geological record of the trench, removed from the ocean and the atmosphere for timescales that dwarf any human consideration. This process, occurring all over the deep ocean floor, is one of the mechanisms by which the Earth regulates its own carbon budget over geological time. The deep ocean is not just a passive recipient of the surface world's activity. It is an active participant in the chemistry of the whole planet. Scientists studying the trench have found evidence that microbes can survive within the sediment itself, deep beneath the seafloor surface. The sediment at the bottom of the Mariana Trench is not a lifeless layer of accumulated material. It is alive, not with the visible creatures that move across its surface, but with microorganisms, bacteria and archaea that live within the sediment, sometimes extending many meters below the seafloor surface, surviving in conditions that make the deep ocean itself seem hospitable by comparison. These deep sediment microbes live in the dark, with little or no oxygen, under extraordinary pressure, with virtually no nutrients. They are among the most extreme organisms on Earth, and also among the most numerous. The number of microbial cells living within the seafloor sediments of the world's oceans is estimated to be comparable to the number of cells in all the plants and animals living on the surface combined. The majority of Earth's biomass, by some calculations, is microbial and lives in the rocks and sediment beneath the ocean floor. These microbes are exquisitely slow. Their metabolism operates at rates almost impossible to measure by ordinary means. Some researchers believe that individual microbial cells in the deep sediment may divide only once every few thousand years, or even less frequently. They are not sleeping. They are simply alive at a pace so slow that time, for them, is a very different thing from what it is for us. To study them, scientists drill down through the sediment and rock, collecting core samples that must be handled with extraordinary care to avoid contamination. And what they find, even meters below the seafloor, is life. Faint, slow, patient, unimaginable life. Still present, still processing chemistry, still being alive in the only way they know how. The unique biology of deep-sea creatures is giving scientists new insights into medicine and biotechnology. Life in the extreme conditions of the deep ocean produces biochemistry that does not exist anywhere else. Enzymes that function at high pressure, proteins that remain stable at near-freezing temperatures, membranes that maintain fluidity under conditions that would solidify the lipids found in most organisms. The chemistry of deep-sea life is a toolkit built by evolution for a very specific and very demanding world. And it turns out that this toolkit has potential applications far beyond the deep ocean. Scientists have been studying deep-sea enzymes with enormous interest, because enzymes that work well at extreme temperatures and pressures often also work well in industrial processes that involve those same conditions. Cold-active enzymes, derived from organisms that live near the freezing point of water, can drive chemical reactions at low temperatures that would normally require heating, saving energy in industrial applications. Deep-sea bacteria have also become a target of medical research. Novel compounds produced by deep-sea microorganisms, compounds that have evolved for purposes unique to their environment, sometimes have remarkable biological activity in human systems. Some have shown promise as antibiotics, anti-cancer compounds, or anti-inflammatory agents. The pharmaceutical industry has been increasingly interested in the biochemistry of the deep ocean as a source of novel molecules. The deep is not just a place of pure scientific curiosity. It is a reservoir of biological innovation accumulated over millions of years of evolution in a uniquely demanding environment. Every species down there is a library of solutions to problems we have not fully understood yet. The way that nutrients cycle in the Mariana Trench differs fundamentally from shallower ocean ecosystems. In the sunlit surface ocean, nutrients cycle relatively quickly. Phytoplankton absorb nutrients and grow. They are eaten. Their predators are eaten. Eventually, nutrients return to the water through excretion and decomposition. The cycle turns over in weeks or months. In the Mariana Trench, the cycling of nutrients is entirely different. The organisms down there receive their nutrients from above, in the form of organic material that sinks from the sunlit zone. This material arrives slowly and irregularly. It is not a steady supply, but a gradual, unpredictable rain. The organisms of the deep have evolved to make the most of whatever arrives. When something does arrive, the response can be dramatic. A large piece of organic material landing on the trench floor is rapidly colonized by bacteria, which begin breaking it down. Amphipods and other scavengers arrive quickly, drawn by chemical signals in the water. In a matter of days, a carcass that took years to reach the bottom can be consumed almost entirely. But in between these events, the community of the deep must subsist on very little. The bacteria in the sediment process what organic material has been incorporated into the sediment over time. The larger organisms move slowly, conserving energy, waiting for the next delivery from above. It is a life organized around scarcity and patience, around the ability to go without and to make the absolute most of what comes when it does. The Mariana Trench has been designated part of a United States national monument, protecting it from exploitation. In 2009, President George W. Bush established the Marianas Trench Marine National Monument, protecting the waters and seafloor of the Mariana Trench and the surrounding area. The monument encompasses the Mariana Trench itself and the volcanic arc and islands associated with the subduction zone. The creation of the monument reflected a growing recognition that the deep ocean, long considered too remote and extreme to need protection, was in fact vulnerable to human activity. Deep-sea mining interests had begun to look at the mineral-rich hydrothermal vents and seafloor sediments as potential sources of valuable metals. Fishing operations had demonstrated the capacity to impact even very deep populations of certain species, and the accumulation of pollutants in deep-sea organisms, including in the Mariana Trench itself, showed that human influence could reach even the most remote corners of the ocean. The monument designation does not mean the trench is closed to scientific research. Research expeditions can still obtain permits to visit and study the area. What it does prevent is commercial exploitation of the trench's resources. No mining, no commercial fishing. The trench, within the boundaries of the monument, is protected as a natural area. It is a small measure of acknowledgement from the surface world that the deep deserves to be left largely to itself, that the patience of the trench, which has existed for tens of millions of years without human intervention, is worth honoring. Microbial mats cover large areas of the trench floor and serve as a foundation for other life. In many parts of the trench floor and in the areas surrounding hydrothermal vents and cold seeps, thick mats of bacteria cover the sediment. These microbial mats are sometimes visible in the footage collected by remotely operated vehicles, appearing as pale or orange-colored films on the seafloor. They can extend for considerable distances, blanketing the sediment in a living layer. The bacteria in these mats are the primary producers of the deep. They are not photosynthetic, but chemosynthetic, using chemical energy from the compounds around them to produce organic material. Other organisms feed on the mats, grazing across them the way animals on land graze on grass. Small crustaceans pick through the mat. Worms burrow through it. The mat provides both food and habitat for a community of small organisms that would not otherwise survive. Microbial mats are ancient. They are the direct descendants of the earliest communities of life on Earth, which grew as mats in shallow seas more than 3 billion years ago. In the deep ocean, far from the evolutionary pressure that drove so many groups of organisms to develop complex bodies and specialized behaviors, microbial mats have persisted essentially unchanged for eons. They are, in the most literal sense, the oldest form of life on Earth, still doing what they have always done, in the darkness at the bottom of the sea. There is something profoundly settling about that. The same kind of life that was present when our planet was young is still present at the bottom of the Mariana Trench, living in the dark, turning chemistry into existence, patient beyond any human measure of patience. Scientists use specially designed pressure vessels to study deep-sea organisms in conditions that mimic their natural habitat. One of the great challenges of deep-sea biology is studying organisms that cannot survive the change from their natural environment to the surface. Most deep-sea creatures, caught in a net or a trap and brought to the surface, do not survive. The change in pressure is too rapid, too extreme. The organisms effectively decompress, their tissues unable to maintain their structure in the very different conditions of the surface ocean. To address this, engineers and scientists have developed specially designed pressure vessels that allow deep-sea organisms to be kept alive under conditions that mimic their natural habitat. These vessels maintain high pressure and low temperature, and allow researchers to observe the behavior of deep-sea organisms under controlled conditions. The results of this work have been illuminating. Deep-sea amphipods, kept at high pressure in a laboratory, can be observed feeding, moving, and reproducing. Their behavior at depth turns out to be quite different from their behavior at reduced pressure. They are more active, they feed more efficiently, they navigate differently. The laboratory conditions that reveal the most about them are the conditions that most closely match the bottom of the trench. Deep-sea bacteria cultured at high pressure produce different compounds, grow at different rates, and behave differently in almost every measurable way than they do at surface pressure. They are literally different organisms, in functional terms, at depth than at the surface. The pressure is not just a background condition. It is a fundamental part of what they are. The ocean floors of the world's deep trenches remain among the most pristine environments on Earth. Despite the evidence of pollution that has been found even in the Mariana Trench, the deep ocean floors remain among the least disturbed environments on our planet. No roads have been built through them. No forests have been cleared. No agricultural chemicals have been applied to them. No cities sit above them. The vast majority of the deep ocean floor has never been seen, never been sampled, never been touched. This pristineness is, in part, simply a result of inaccessibility. The deep ocean is hard to reach and expensive to study. Its remoteness has protected it from most human activity by default, not by intention. But the result is that we still have, on our own planet, environments that are as close to undisturbed as any wild place on Earth. The species that live in those environments have not been subjected to hunting, to habitat destruction, to the introduction of invasive species, to all the pressures that have devastated so many surface ecosystems. They live in the context for which they evolved, surrounded by the conditions they have always known. That is increasingly rare. Much of the surface world has been changed by human activity to a degree that makes it hard to see what it was before. But the deep ocean still gives us a glimpse, a view of life functioning in its own terms, in its own time, in its own darkness, as it has for millions of years. That glimpse is precious, and we would do well to protect it. Some deep-sea fish have eyes adapted to detect even the faintest traces of bioluminescence. In a world where the only light is produced by the creatures themselves, eyes have evolved to detect extraordinarily small amounts of it. Many deep-sea fish have enormous eyes relative to their body size, large visual surfaces that gather every available photon. But size alone is not the only adaptation. The visual pigments in deep-sea fish eyes have shifted to be most sensitive to the wavelengths of bioluminescence common in their environment. Since most bioluminescence in the deep ocean is blue or blue-green, the visual systems of deep-sea fish are tuned to those colors. They are, in essence, specialist instruments for detecting the specific quality of light produced by the organisms around them. Some deep-sea fish can detect light at levels so low that they border on the physically impossible for any biological system. They see in conditions that are essentially dark by any surface standard. A single photon arriving at the right receptor can trigger a response. These animals are living at the edge of what is physically possible for vision. And yet what they see, presumably, is a world of intermittent flickers and glows. A cold, blue-tinged world punctuated by brief sparks of light. The steady bioluminescence of a nearby organism. The sudden flash of a startled creature. The steady glow of a lure dangling in the dark. Not much, but enough. Enough to navigate by, to hunt by, to avoid being hunted by. Enough to live in the dark. The deep ocean has inspired some of humanity's most enduring myths about monsters and mystery. Long before science had any understanding of what lived in the deep ocean, people knew that the sea had depths beyond imagining. The ocean was vast and dark and unknowable, and from that darkness, the imagination conjured creatures of extraordinary scale and menace. Sea serpents, kraken, leviathan. The monsters of myth were, in many ways, expressions of the same feeling that drives scientists today into the deep. The knowledge that something extraordinary is down there, beyond the reach of ordinary sight. The kraken of Norse mythology was imagined as a creature so enormous it could be mistaken for an island, pulling ships down into the deep with arms wide as a sailing vessel. The sea serpents of medieval maps, labeled with the words meaning, "Here there be dragons," were the cartographic expression of genuine uncertainty. The ocean's depths were real. What lived in them was unknown, and the unknown, for a storytelling species, is never left empty. Place. It turns out that the deep ocean does contain creatures of remarkable and sometimes unsettling form. The giant squid, long the subject of sailors' tales, is real. It can reach lengths of over 12 meters. It has the largest eyes of any known animal, eyes as large as dinner plates, adapted to detect bioluminescence in the deep. It has been seen alive only rarely, and most of what we know about it comes from specimens found in the stomachs of sperm whales. The anglerfish, with its nightmarish bioluminescent lure and its extraordinary sexual dimorphism, is real. The viperfish, with its teeth so long it cannot close its mouth, is real. The barrel-eye fish, with transparent fluid-filled domes over its eyes, is real. The deep ocean has provided, repeatedly, creatures that would seem fantastical if they were not documented by cameras and scientific collection. The monsters were, in their way, correct. The deep ocean does contain wonders. They are simply different from the ones we imagined. The Mariana Trench reminds us that our knowledge of our own planet is still very incomplete. It is easy, in the age of satellite imagery and global communication, to feel that the Earth has been fully mapped and fully known. We can look at our planet from space. We can zoom in on any point on the land surface with resolution fine enough to see individual buildings. We can track the movement of weather systems across entire continents in real time. The surface world is known to us in extraordinary detail. And yet, below the surface of the ocean, which covers more than 70% of the planet, lies a world that is largely unmapped and almost entirely unvisited. We have measured the shape of the ocean floor with sonar, but our maps lack the resolution to show features smaller than a few hundred meters. The detailed topography, the geology, the biology, the chemistry of most of the ocean floor is essentially unknown. The Mariana Trench is a reminder of the scale of our ignorance, not as an accusation, not as a source of shame, but simply as a fact. The world is larger than our knowledge of it. There is more to discover than has been discovered. The frontier is real, and it is here, on our own planet, beneath our feet. That is, in the quiet hours of the night, a beautiful thought. Not everything is known. Not everything has been seen. There is still mystery in the world. There are still places that have never been witnessed by human eyes, that carry their wonders in complete privacy, that exist entirely on their own terms. The Mariana Trench is the deepest of these places, but it is not the only one. The world is full of depths, and all of them are worth approaching with patience and wonder and a willingness to be surprised. The deep ocean has its own seasonal patterns, driven by events far above at the surface. We tend to think of seasons as a surface phenomenon: the tilt of the earth, the changing angle of the sun, the warming and cooling of the air, the blooming of plants, and the migration of animals. All of it plays out in the world of light and weather. But the deep ocean has its own relationship with the seasons, indirect and delayed, mediated by the long journey from the surface to the bottom. In spring and summer in the productive ocean regions, the sunlit surface waters bloom with phytoplankton. The abundance of food at the surface drives an abundance of animal life. And all of those organisms, as they live and die and shed waste, contribute to the marine snow that sinks toward the bottom. When the surface blooms, the amount of organic material reaching the deep floor increases. When the surface quiets in winter, the delivery slows. The deep community feels this. Not immediately. The particles take weeks or months to sink from the surface to the bottom. The signal is delayed and diffused by the journey, but it arrives. The organisms of the deep floor have been found to show seasonal patterns in their feeding behavior and their population dynamics, responding to the annual pulse of organic material from the world above. It is a remarkable kind of connection. The deep floor, in permanent darkness, in steady cold, somehow tuned to the rhythm of a sun it has never seen, receiving signals from a world of seasons that is entirely foreign to its own experience. The surface and the deep, so different, so separated, in quiet communication through the slow fall of particles. The geology beneath the Mariana Trench is some of the oldest oceanic crust on Earth. The crust that forms the floor of the Western Pacific Ocean is among the oldest oceanic crust on Earth. Unlike continental crust, which can persist for billions of years, oceanic crust is continuously recycled. New crust is created at mid-ocean ridges, where magma wells up from below, and old crust is destroyed at subduction zones, where it dives back into the Earth's interior. The Pacific Plate, which is being subducted at the Mariana Trench, carries crust that formed at mid-ocean ridges as long as 180 million years ago during the Jurassic period. That means the rock that is currently sliding beneath the Mariana Plate, carrying the floor of the trench down into the Earth, was created when dinosaurs were still alive and when the continents were arranged in configurations completely different from their present positions. The trench, in a sense, is a machine for destroying ancient geology. The old, dense Pacific crust descends into the Earth's interior, where it is melted and reincorporated into the mantle. The water it carries with it, trapped in the minerals of the seafloor sediment, is released into the overlying rock, driving volcanic activity. The chain of volcanic islands visible at the surface, the Marianas themselves, is the direct result of this process. The old crust goes down, new volcanic rock comes up. Destruction and creation, the same process, the same place, operating for 180 million years, patiently, without interruption. Deep-sea creatures that drift upward to shallower depths often die from the pressure change, showing how precisely adapted they are. The adaptation of deep-sea creatures to their environment is not just functional, it is total. There is no degree of freedom in it, no flexibility, no capacity to live in any other world. A snailfish at 8,000 meters is not merely comfortable there. It is made for that depth and no other. Move it upward, even a few hundred meters, and its biochemistry begins to fail. This is why so few deep-sea organisms are ever seen alive at the surface. Occasionally, a creature from intermediate depths will be found floating at the surface, washed up on a beach, or encountered by a ship. It is almost always dead or dying, its tissues failing in the lower pressure environment, its internal chemistry unable to function correctly so far from home. The Xenophyophores fall apart on the way up. The snailfish dissolve. The amphipods stop functioning. Each organism is so precisely calibrated to its own depth that any significant departure is fatal. They cannot explore. They cannot migrate upward to see what lies above. They are fixed in their world as firmly as if they were embedded in the rock. In one sense, this seems like a limitation, but in another, it is the purest form of belonging. These organisms do not need to be anywhere else. They do not seek another environment. They have found, through millions of years of evolution, the exact conditions that suit them perfectly, and they stay there, perfectly at home, in the dark and the cold and the immense, patient pressure. The quiet of the deep ocean is a silence with no equal on the surface of the Earth. There are quiet places on the surface of the Earth. A library, late at night. A forest, after heavy snow. A desert, at 3 in the morning, far from any road. A mountain lake, on a windless day in autumn. These are places where the noise of human civilization fades, and you can hear something closer to the original quiet of the world. But even the quietest places on the surface of the Earth carry sound. The movement of air, the ticking of cooling rocks, the distant rumble of the planet's machinery. And at night, The sounds that you only hear when everything else is still. Insects, the creak of a tree, the very faint and distant sound of human activity carried on the wind. The bottom of the Mariana Trench is quieter than any of these. Not because it is silent, because, as we have said, sound travels easily through water and the trench receives echoes from far above. But it is quieter in a different way. There is no wind at the bottom of the trench, because wind is a surface phenomenon. There is no air. There are no insects, no rustling vegetation, no creak of expanding or contracting material warmed by a sun that cannot reach. The sounds of the deep are water sounds, the passage of distant earthquakes through the rock, the slow movement of deep currents, the soft disturbances made by creatures moving across the sediment. And above it all, from unimaginable distances, the faint echoes of a world that seems, from the bottom, very far away. It is the sound of a place that has found its own peace, deep in the dark, at the bottom of everything, in a quiet that has persisted for longer than any of us can imagine. That quiet is there right now. As you rest, as the world around you settles, as your breath slows and your thoughts soften, that quiet is at the bottom of the Pacific, unchanged and unchanging. Some quietnesses are bigger than others, some go deeper, and the deepest quiet on Earth rests at the bottom of the Mariana Trench, patient and perfect, where it has always been. The deep ocean will continue to be explored, and every expedition adds to a story that is still being written. There is no end to the Mariana Trench story. It is still being written by the scientists who study it, the engineers who build the vehicles that descend into it, the biologists who catalog its creatures, the chemists who analyze its sediment, the geologists who map its shape. And it is being written by the trench itself, by the tectonic forces still reshaping its floor, by the organisms still adapting to its extremes, by the water still circulating through its darkness on timescales of centuries. Every time we lower a camera into the deep, we see something that has never been seen before. There is a particular kind of scientific moment that is almost impossible to describe to someone who has not experienced it. It is the moment when an image arrives from somewhere it has never come from before. When a camera on a remotely operated vehicle reaches the bottom of an unexplored section of the trench, and the screen in the control room on the ship above begins to show a landscape that no human eye has ever looked upon. The researchers watching that screen see sediment, and perhaps ridges of rock, and perhaps nothing obvious at first. And then, something moves. An animal, unknown or poorly known, going about its life with complete indifference to the machine that has just arrived to watch it. The researchers lean forward. Someone reaches for a notebook. Someone begins to record. A conversation starts, quietly, about what they are looking at, what it might be, whether it has been documented before. This happens on virtually every deep-sea expedition that reaches unexplored territory, not always dramatically. Sometimes the new thing is a species already known from other trenches, now confirmed at a new location. Sometimes it is a behavior not previously documented. Sometimes it is a creature that no one in the room can immediately identify, and that will require months of analysis by specialists before it is understood. But it happens. The deep keeps giving, and every new image, every new sample, every new data point is a brick in the edifice of knowledge that humanity is slowly, patiently, expedition by expedition, building about the most extreme environment on our own planet. Future generations will know things about the Mariana Trench that we cannot imagine. The technology will improve. The visits will become more frequent. The biology and the geology and the chemistry will be mapped in greater and greater detail. And still, in all likelihood, there will be more to discover. The deep is large enough and complex enough and patient enough to sustain our curiosity. for as long as we choose to exercise it. In the meantime, what we have is remarkable. A place 11 kilometers below the surface. A world of darkness and pressure and cold that has existed for tens of millions of years. A community of creatures adapted to conditions unlike anything else on Earth. A geological process of enormous power and patience. An archive of planetary history written in sediment. All of it sitting quietly at the bottom of the Pacific Ocean. Right now, as you rest, the deep is there. It has always been there. And in the quiet of the night, knowing it exists, knowing it is there beneath the ocean's skin, patient and full and entirely itself, is a comfort of a very particular kind. The kind that comes from knowing that the world is larger than we think, and more full of wonders, and more full of life, and more capable of surprise. We did not choose to live on a planet with such a deep and extraordinary place beneath its oceans. But we do, and it is there for us to think about on the nights when thinking about something vast and calm and unhurried is exactly what is needed. The Mariana Trench, 11 kilometers down, in the dark, in the cold, full of life and geology and chemistry and mystery, is exactly that kind of vastness, exactly that kind of calm. The trench has heard none of our noise. It has felt none of our urgency. It has not been touched by our seasons or our centuries. And yet, in knowing it, in holding the idea of it in the mind on a quiet night, something in us responds to it. Something recognizes the value of that depth and that stillness. Something in us is grateful, deeply and quietly grateful, that such a place exists. That not everything on this planet moves at our speed, or asks to be seen, or needs anything from us at all. The trench is just there, waiting, patient, complete. And so, tonight, are you. The next expedition will find something new. It will always find something new. The deep ocean is not the kind of place that runs out of surprises. It is the kind of place that generates them quietly and persistently from a depth of possibility that has not been exhausted in millions of years. And all of that is happening right now as you rest here, down at the bottom of the Pacific, in a darkness you will never see, in a cold you will never feel. Creatures are moving, chemistry is happening. The Earth's plates are shifting by millimeters. Sediment is drifting down, particle by particle, adding another infinitesimal layer to the archive of the deep. The trench does not sleep, but it is wonderfully, profoundly quiet. And in that quiet, there is something that makes our own rest feel very natural, very right. The deepest place on Earth rests in its own kind of stillness, and in the dark hours of the night, we can rest along with it. And so, dear listener, we have traveled together to a place that is both impossibly remote and somehow intimately connected to everything we are and everything our planet is. We have descended, slowly and gently, through the layers of the ocean, through the sunlit surface where waves catch the light, through the twilight zone where daylight fades to blue, through the midnight zone where darkness becomes total, all the way to the floor of the Challenger Deep, the deepest, strangest, most patient place on Earth. We have met the snailfish, pale and soft, perfectly shaped for depths that would destroy everything we are familiar with. We have drifted with the amphipods in their countless thousands, moving through the cold and the dark with calm efficiency. We have rested in the sediment, listening to the slow accumulation of millions of years. We have felt, in a quiet way, the weight of all that water above us, pressing down not with violence, but with a steady, ancient calm. The trench has been there for tens of millions of years. It will be there for tens of millions more. The plates will continue to move. The sediment will continue to fall. The creatures of the deep will continue to live their unlit lives with extraordinary grace and patience. And the ocean above will continue to carry its storms and its currents and its light. And none of it will reach the bottom. And the bottom will not mind. There is a lesson in that, perhaps, a kind of permission. The world above is always moving, always lit, always asking something of us. But the deepest thing we know exists in its own quietness, at its own pace, on its own terms. And everything is well down there. Everything is exactly as it should be. Let that image carry you now. The pale floor of the Challenger Deep, soft with sediment, still and cool. The faint shimmer of a bioluminescent creature drifting through the dark. The slow fall of particles from a world too distant to see. The patient, unhurried presence of the oldest, deepest, most steadfast place on Earth. Let your breath slow to match it. Let the weight of the day settle downward, the way sediment settles, gently and without hurry, finding its place on the floor of something vast and quiet and entirely at rest. You are safe here. The deep holds you. The ocean holds you. The whole enormous, extraordinary planet holds you, as it has always held you, without effort and without end. Close your eyes, breathe slowly, and drift, as everything drifts in the deep, gently downward, into stillness, into silence, into the soft, dark, where nothing is asked of you and everything is well. Good night.